Hello there and welcome back to the Sleep Science. Tonight, the stars don't just twinkle, they watch you. You're floating far from Earth now, far enough that the familiar constellations have shifted into strange new shapes. The Milky Way stretches overhead like spilled silver dust, and the dark between its arms feels deeper than anything you've ever tried to look into. Somewhere out here, a pair of invisible monsters circles each other, warping the very stage they dance upon. You probably won't survive this, but let's be honest, you didn't come this far for safety. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're here, drop your location and your local time in the comments. Let's see how far this little nighttime voyage reaches. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Your first sensation is the quiet, not the absence of sound exactly, because in the vacuum of space, sound isn't a thing, but a sort of felt silence pressing against your awareness. Behind you, light from a nearby red giant is fading as the star nears its death, its outer layers peeling away into space like wisps of campfire smoke. In ancient China, astronomers might have marked this star's dimming on parchment, nodding it as an omen. Historians still argue whether such records describe supernovae or something else entirely. Ahead, there's something stranger. The space in front of you seems wrong. Stars behind it smear and bend like reflections in a funhouse mirror, their light detouring around something that refuses to be seen directly. You're looking at gravitational lensing, Einstein's once wild idea that massive objects bend space so much that light must curve to get around them. Here, it's happening because of a black hole. This one isn't alone. A flicker to your left, more distorted starlight. Another hole. Both are silent, invisible, but the geometry of the void around them betrays their positions. They're moving slowly as though testing each other's pull. It's like stumbling on two ice skaters who have locked eyes across the rink, except their skates are carving through spacetime itself. You drift closer, careful not to cross the invisible line, the event horizon beyond which escape is impossible. If you did, you'd be crushed into something far less glamorous than stardust. The weird thing, from your vantage point you can't see the black holes themselves, only the consequences of their existence. Gas and dust in the area swirl in luminous arcs, heated to near incandescence as they fall inward. That bright disk, it's called the accretion disk. In medieval Europe, such a sight might have been interpreted as a literal hole to heaven or hell. One of the quirks about watching black holes from this distance is that time seems honest. Your seconds match theirs. But if you were to fall toward one, your seconds would stretch into hours, days, centuries, depending on who's watching. That's relativity for you, a cosmic prank that's also one of the most rigorously tested ideas in science. And yet here, floating between these two invisible predators, you feel time as a steady pulse, even as theirs subtly distorts. They aren't rushing toward each other. This dance could take millions of years to finish, but gravitational waves, the ripples in spacetime Einstein predicted in 1916, are already leaking from their orbit. They carry away energy, shrinking the distance between the pair ever so slightly. You can't hear them with your ears, but if your body were somehow a detector the size of Earth, you'd feel a faint, regular shiver in your bones. For now, you just watch. The black holes circle, locked together by a force so absolute it has no rival. Somewhere in the back of your mind, you remember reading that even black holes themselves can't escape this fate. If one gets caught in another's gravitational embrace, the outcome is inevitable. The only question is how long it will take. And as you float in that silent gulf, you feel it, that peculiar human mix of fear and fascination. These things can swallow stars whole, erase light, and twist reality itself. And yet, you're drawn closer, as if part of you wants to see what happens when the universe decides two infinities should become one. You keep drifting, the darkness deepening, the warped stars behind you stretching like molten glass. Out here, black hole isn't just a scary sci-fi term. It's a literal region of spacetime where gravity wins against everything. No matter how fast you run, swim, or scream photons at full tilt, you won't make it out once you've crossed the event horizon. That's not poetic exaggeration, it's physics at its most absolute. The name itself is misleading. Black makes sense, you can't see one directly, but hole suggests some kind of tunnel or empty pit. In truth, a black hole isn't hollow. It's an object collapsed so densely that all its mass is squeezed into a point of effectively zero volume. That point is called a singularity. Astronomers still argue whether the singularity is a physical reality or just the mathematical equivalent of a shrug. Either way, it's the ultimate no-return address in the cosmos. You hover just far enough away to stay safe, your imaginary safety line wrapped tightly around the edge of the accretion disk. If you were to peer with X-ray eyes, you'd see the disk blazing, hotter than the core of most stars, as infalling matter slams together at ridiculous speeds. The light from that frenzy is the only reason astronomers ever found these things. In fact, it was 18th century thinker John Michell who first imagined an object so massive even light couldn't escape. He called them dark stars. He had no proof, but his mental blueprint wasn't far from reality. Here's the quirky part. Black holes aren't all born the same way. Most of the ones you'll meet tonight started life as massive stars, 10 or 20 times heavier than our sun. When such a star runs out of nuclear fuel, its own gravity wins the arm-wrestling match, crushing it into a black hole in seconds. Others form when smaller black holes merge, a kind of cosmic Lego process. Then there are the true beasts, supermassive black holes, millions to billions of times heavier than the sun, squatting at the center of nearly every galaxy we've looked at. How those giants formed, still an open question. You imagine your two silent companions from before, stellar mass black holes, most likely, quietly circling each other. Their gravity is immense but localized. If you swap them for a single supermassive black hole, you could place our entire solar system comfortably inside its event horizon. Comfortably, of course, being a relative term. The boundary between their space and yours isn't marked by a wall or a glowing ring of "you shall not pass." Instead, it's an invisible spherical surface where escape velocity, the speed you'd need to break free, equals the speed of light. That's the event horizon. If you're outside it, you can, in theory, leave. Inside, you'd need to go faster than light, and the universe has a very strict policy against that. It's tempting to think of them as monsters, but black holes don't hunt. They don't move through the galaxy like vacuum cleaners, sucking up everything in their path. They simply sit, and if something, gas, dust, stars, unlucky spacecraft, wanders too close, gravity does the rest. If our sun were replaced by a black hole of the same mass, Earth's orbit wouldn't change a bit. We'd just be cold, dark, and very, very bored. Still, they have personality in a way. Black holes have only three measurable properties: mass, spin, and electric charge. Most are electrically neutral, but mass and spin, those shape their surroundings. A rapidly spinning black hole drags spacetime with it, a phenomenon called frame dragging, which can fling infalling matter into jets streaming out at near light speed. Yes, the very thing designed to swallow everything can also spit matter out, if only before it crosses the horizon. As you drift in this quiet vigil, you notice the lensing again, starlight bending around their unseen bodies. It's a distortion so perfect it would make a Renaissance painter weep, the kind of trick the universe pulls without asking your opinion first. If you could somehow fall toward one while still looking out, the entire universe would seem to shrink into a glowing ring behind you. Not that I recommend testing it. Your mind wanders to the sheer scale. The smallest known black hole is only about 3 times the sun's mass, barely larger than a city. The largest, roughly 66 billion solar masses, sitting in a galaxy 5 billion light-years away. That one could swallow our Milky Way and still have room for dessert. Historians still argue whether medieval Arabic sky charts hint at such massive central objects, though it's more likely they were simply recording bright stars and nebulae. The two before you are far humbler but no less captivating. Right now, They're in a long-term relationship defined entirely by the laws of physics: spin, mass, and gravitational attraction. Slowly, imperceptibly, they're being drawn together by the spacetime ripples they create. Over eons, those ripples will drain away enough orbital energy that one day they'll meet. When they do, you'll get a burst of gravitational waves that could shake detectors across the cosmos. But for now, you keep watching, suspended in the void. Two invisible titans, locked in a silent loop, writing their shared future in the fabric of spacetime. The deeper you drift into this gravity-twisted pocket of the universe, the more the invisible force holding everything together starts to feel personal. Gravity isn't just things falling down anymore. It's the sculptor of galaxies, the silent puppeteer pulling on every particle of matter you've ever seen. It's what turned hydrogen into stars, what made those stars die, and what now binds two invisible corpses into a cosmic waltz that could last longer than humanity has existed. On Earth, gravity is mostly predictable. It keeps your coffee mug on the table, your shoes on the ground, and your cat determined to knock both onto the floor. But in the realm of black holes, gravity stops being that familiar downward tug. It becomes a curvature of space itself, wrapping the cosmic stage into strange shapes that light, time, and matter must follow. Einstein's general theory of relativity replaced the old Newtonian picture with a weirder, more beautiful one. Instead of imagining gravity as a force reaching across space, picture space as a stretchy fabric. Mass tells that fabric how to curve, and curved fabric tells mass how to move. Drop a bowling ball onto a trampoline and a marble will spiral toward it, not because the ball is pulling it, but because the surface it rolls on is warped. Black holes. They're the bowling balls so heavy they punch a hole right through the trampoline. That hole is what makes their pull so relentless. Once you cross that point of no return line, it's not that you can't escape because gravity is too strong. It's that every possible path forward leads inward. Even light's best option is just to circle for a moment before sliding in. You remember those two silent companions orbiting each other ahead. They aren't tugging each other like two magnets. They're reshaping the spacetime between them so drastically that each one slides endlessly toward the other. At their distance, this motion is slow. In fact, if you could somehow stop time and paint their positions onto the cosmic backdrop, you might think nothing's happening at all. But zoom forward a few million years and you'd see their dance tighten, their orbits shrinking like a noose. There's a quirky fact that makes you smile in the middle of all this cosmic seriousness. We technically fall toward the sun at all times, but Earth's sideways velocity is so perfect that we miss it continuously. Like being in perpetual free fall around a campfire you never quite tumble into. With black holes, it's the same, just on a scale that makes our solar system look like a marble in a swimming pool. Gravity here also plays strange tricks with time. In this distorted spacetime, clocks closer to the black hole tick slower compared to those far away. Imagine visiting a friend's house near the event horizon. You spend an hour chatting, but when you head home, everyone you know is decades older. Historians still argue whether certain ancient myths about people visiting other realms and returning centuries later might be poetic echoes of humanity's innate suspicion that time isn't as steady as it seems. The really mind-bending part, from where you float now, watching these two black holes approach each other, you can measure their movement not in kilometers per second but in how spacetime itself flexes. They're pulling each other along not through emptiness, but through a warped, dynamic medium. You try to visualize it, the spacetime grid around them twisting, bending inward, the lines tightening with each orbit. As the black holes spiral closer over cosmic ages, their dance will accelerate. Their gravitational field will begin to shed more and more energy in the form of ripples, gravitational waves, until they collide in a burst of spacetime distortion so powerful it will race across the universe at light speed. But right now, there's only the quiet, steady hum of potential energy. It's like watching two storm fronts on opposite horizons, knowing one day they'll meet and the sky will tear open. You drift in this thought for a long time. No rush. After all, time itself is elastic here. You watch the two shapes of absence circle each other, their presence visible only in what they do to everything else. The smeared starlight, the shimmering arcs of lensing, the way time feels like a carpet someone's tugging under your feet. It isn't a crash, it's a courtship. Slow, ceremonial, patient to the point of comedy, as if the universe set up a candle-lit dinner and then forgot to put the candles out for a few million years. They drift together not by choice, not by hunger, but because spacetime itself keeps rearranging the furniture beneath them until closer becomes the only choreography left. At first, the orbit is wide and lazy. If you could mark their positions with glowing dots and revisit the scene every 1,000 years, you'd swear nothing had changed. But at each pass, each sweep through periastron, their closest approach, some energy sighs away as gravitational waves. The orbit shrinks imperceptibly at first, like a belt tightened one hole every century. Their dance isn't a perfect circle either. Frame dragging and relativistic precession twist the ellipse so the closest point keeps marching around. It's a waltz that draws its own spiral on the dance floor. You can almost hear it. Not music exactly, but that imagined chirp scientists love to play back. The frequency rising so gently you mistake it for the soft whir of your bedroom fan. There might be gas here, a faint, ragged circumbinary disk that orbits both giants at once, like a satin ribbon tossed across the floor. Streams can peel off that ribbon, feeding minidisks around each black hole. Those streams crash in heat, flicker in X-rays, and for a blink they paint each partner with a glowing collar. If one is spinning fast and tilted, the collar can wobble, and a weak jet might squint and precess, sweeping a lighthouse arc across nothingness. You watch that beam graze a star field and think of someone waving a flashlight through fog, insisting there's a path where your eyes say there is. A mainstream breadcrumb flickers in your memory. In 1974, Russell Hulse and Joseph Taylor found a pair of neutron stars locked in a tight orbit, PSR B1913+16. They weren't black holes, but their period was shrinking exactly as Einstein's equations predicted, energy leaking away in gravitational waves. No detector had heard the waves yet, but the orbital decay was a dead giveaway. They eventually won the 1993 Nobel Prize, and the cosmos offered a polite "told you so." Now you're watching the black hole version of that inevitability, writ darker and bigger. Up close, not too close, you notice how unequal partners change the mood. If one black hole is heavier, it sits nearer the system's center of mass while the lighter one sweeps a wider track, like a ballroom dancer doing most of the cardio while their partner maintains suspiciously serene eye contact. Depending on their spins, the orbital plane can precess, a slow hula hoop wobble carved into spacetime. When the spins are misaligned, the whole system torso twists, and the gravitational waves that leak out carry that wobble like a secret handshake. Astrophysicists still argue whether most merging pairs arrive here as old married couples, born from a duo of massive stars aging together, or meet later at a raucous party in a star cluster, captured by chaotic three-body encounters that leave the third wheel flung into the void. There's a quirky tidbit your brain refuses to let go. Near the plunge, or if the orbit stays eccentric, the lighter partner can execute zoom-whirl orbits, long stretch sweeps far away, then dizzying tight loops near the heavier one, like a moth making questionable life choices around a porch light. For a few cycles, the path rosettes, drawing petals that no one will ever see except as a pattern etched into the outgoing waves. It's celestial calligraphy signed with no ink, only curvature. You practice being calm, letting time's rubber band stretch. Each pass is a little faster, each separation a little smaller. The energy sluicing away into the fabric of reality itself is so ridiculous your inner accountant quietly resigns. You picture the orbit like a bathtub drain, and yes, it's the oldest analogy, but tonight it feels right. The swirl tightens, the surface dips, and the center is no place at all. You also feel how unfussy this is. No fireworks you can see with human eyes, no glitter. The spectacle is mostly math happening in the dark, yet the consequences ripple across absurd distances. Somewhere, eons and light years away, a future astronomer will set a detector humming and listen to the instant you are witnessing, like finding a seashell and hearing the tide of a beach that no longer exists. Some details turn practical. If there's still gas swirling around them, tidal torques carve a gap in the circumbinary disk. Think of two dogs on a leash carving a groove through snow. Streams bridge the gap, the minidisks flare, then starve, then refill in a rhythm that could, in principle, be spotted as periodic brightening. You imagine logging data and labeling peaks. Date night, date night, date night, like your telescope is a nosy neighbor. And yes, at this stage, your cosmic romance metaphor quota is officially maxed out. But tell that to two objects whose fate is basically slow dancing forever. Beyond romance, there's drift and delay. The final parsec problem lurks like a relationship counselor nobody wants to see. Will the pair stall at a separation so large that gravitational radiation can't finish the job in a reasonable cosmic time? In galaxies, stars and gas are supposed to carry away angular momentum through encounters and friction, shrinking the orbit until waves take over. Sometimes it works like a charm. Sometimes simulations throw their hands up and leave the couple awkwardly orbiting like roommates who won't talk about it. Whether real galaxies solve this neatly or need help from trios, gas, or lucky kicks remains one of those dinner table debates. A thread of history glints again. When Einstein first wrote down the field equations in 1915, he didn't imagine you here, counting imaginary minidisks while pretending not to be nervous. He worried whether gravitational waves were even real solutions or just math's mischievous graffiti. Decades of arguments followed. Yes, literal papers volleyed back and forth, until the physics community largely converged that the waves carry energy and momentum and should be detectable. You're floating in the afterglow of that intellectual stubbornness, proof that sometimes the universe waits patiently while we argue on paper. As the orbit tightens, the period drops. Hours become minutes. Minutes will become seconds. That isn't for now, but it's coming, like the end of a song where the drummer, the bassist, and the guitarist all glance at one another and decide to sprint. If they have appreciable spins, you'll get precession modulating the final measures, a warble in the waveform that lets scientists later reconstruct who spun how fast and which way. Imagine reconstructing a dance from the grooves left in the floorboards. That's the job, to read scuffs in spacetime and say, "Ah, so you dipped on the 3." You realize something quietly funny about yourself. You're rooting for them, two gravity wells that would happily turn you into informational pizza if you got cocky. You cheer for the elegance, for the consistency, for that feeling when a prediction and a measurement click into place like magnets. You also cheer for the melodrama, because you are, after all, a human who likes a good story. The universe obliges, telling one with no dialogue, no actors' faces, and somehow all the feelings anyway. You take one last inventory of the courtship stage. The slowness, the tidal streams, the precession, the delicate theft of energy by waves. Far away, someone will call this an inspiral, which sounds like an app that improves your calendar. Here, it feels like what it is. A spiral you can't walk back down, etched by two giants who never touch in the ordinary sense, yet commit to a union so thorough that even light can't announce the vows. Before the sprint, there's a pause. It's not real, nothing halts, but your mind inserts it, the way a crowd hushes as the orchestra lifts bows and the conductor's hands rise. You float in that hush, smiling despite yourself, because the next part is messy and swift and glorious in a way only gravity can be. And if you're keeping score, yes, this is also where you remind yourself not to cross any horizons in the excitement. No autographs from singularities tonight. The pause you imagine breaks, not with a sound. Space still isn't in the habit of giving you audio, but with a change in the rhythm of the starlight around you. The two black holes, still invisible except for their distortions, have reached a stage where their gravitational handshake becomes noticeable, even out here. Not to your ears, but to spacetime itself. Gravitational waves, that's what you're feeling, or rather, what you'd feel if you were an instrument the size of the solar system. Ripples in spacetime radiate outward as the two bodies orbit each other, each orbit a drumbeat that slightly flexes the very medium in which everything exists. These waves aren't like water waves that need something physical to slosh through. They are the sloshing, changes in the geometry of reality itself. The invisible handshake is the simplest metaphor. Every time these two orbit, they trade energy with the universe by shaking spacetime. And unlike your awkward uncle's handshake at family reunions, this one never stops. It keeps tightening, keeps transmitting, until there's nothing left to give. The math says these ripples travel at the speed of light. Einstein proposed their existence in 1916, and for decades, even he waffled about whether they could ever be detected. Historians still argue whether his occasional doubt was genuine skepticism or just a polite shrug to colleagues who found the whole idea unnerving. Either way, it took a full century before humanity heard one. Here's the thing about these waves. They stretch and squeeze space in alternating directions as they pass. If you had a perfect circle of test masses floating in space, a passing wave would turn it into a squashed oval, then a stretched one, over and over, without the masses ever feeling a push in the usual sense. That's because you, the ruler, and the space between the masses are all being distorted together. It's the ultimate inside joke of physics. You can't notice it unless you compare two directions at once. The quirky fact that makes you grin is how absurdly tiny these distortions are. The first gravitational wave detection in 2015 measured a change in length of about 1/10,000th the diameter of a proton, over a 4-kilometer laser arm. That's like measuring the distance to the nearest star and spotting a change smaller than the width of a human hair. And yet, there it was, a ripple born from two black holes merging 1.3 billion years ago. You imagine LIGO, two enormous L-shaped detectors in the U.S., as a sort of cosmic stethoscope. Each arm contains a laser beam bouncing between mirrors in a vacuum tunnel. When a gravitational wave passes, one arm lengthens ever so slightly while the other shortens, changing the interference pattern of the beams. That change, amplified and filtered through a frankly heroic amount of data processing, is how we hear spacetime's music. And the music from black hole mergers is surprisingly distinctive. A low-frequency rumble that rises sharply into a chirp, then cuts off abruptly at the moment of collision. You picture your two dancers ahead, still far from that final chirp, but already sending waves strong enough, if they were just a little closer, to be noticed. They're radiating quadrupole waves, which is the fancy way of saying the distortion they create is lopsided enough to ripple outward. Perfectly symmetrical spinning objects wouldn't radiate at all, boring, silent. But two unequal masses in motion are messy enough to make spacetime sing. And these waves aren't just for show. They carry real energy away from the system, draining the orbital momentum and forcing the two black holes to spiral closer. Without gravitational waves, the pair might just orbit forever, the ultimate will they, won't they scenario. Instead, the waves are the ticking clock of their romance, turning inevitability into a countdown. You drift alongside them and try to imagine what's happening far beyond your location. These ripples are already stretching out across light years, passing through galaxies, dust clouds, and the occasional very confused alien telescope. They don't weaken much over distance. They're like a broadcast that ignores the usual static, carrying the news of this slow-motion collision to any detector in range. Somewhere an exoplanet might have a civilization with its own LIGO equivalent, staring at the same data spike and thinking, two black holes. Guess we're not that special. Even more fun is the idea of space-based detectors, like the upcoming LISA mission, floating millions of kilometers apart, measuring ripples at frequencies too low for ground detectors. Those will catch the slower, more massive dances of supermassive black holes, the kind you find in colliding galaxies. If our two partners here were giants in the millions of solar masses club, Lisa would hear their slow bass notes years before the finale. But here tonight, you're tuned in to the higher-pitched, tighter spirals of stellar mass holes. You know that as the orbit shrinks, the frequency of the waves rises, just like a spinning ice skater pulling in their arms. That rise is encoded in the chirp waveform, a cosmic telltale. Scientists can reverse engineer the mass, spin, and even the distance of the merger just from that shape. It's the most honest form of gossip the universe has. It tells you everything without any visuals at all. You think back to the phrase invisible handshake, and it feels more literal now. The two black holes are indeed exchanging something, not particles, not light, but a pattern of spacetime flexes that can cross billions of light years without ever stopping to ask for directions. It's a handshake that announces itself to anyone with the tools to feel it, a signal that says, "We are here, and soon we will be one." Time starts to slouch. It doesn't stop and it doesn't rebel, nothing so dramatic, but it gets opinionated. Out here, near two merging black holes, seconds become negotiable. Your heartbeat keeps its rhythm, but your clock, if you had one, would be whispering a different tempo than a clock lounging safely far away. Relativity isn't just a clever equation. It's the house rules of this neighborhood, and time is the fussiest neighbor on the block. You let your gaze follow the pair, the slow whirl that's been tightening since the first invisible handshake. As they circle, the metric, the mathematical recipe for distances and durations, warps. Your proper time, the time your body experiences, keeps streaming forward like a calm river. But coordinate time, the time someone far from any gravity would use to label events, stretches and folds. Stand too near the event horizon, and the river becomes syrup. From the outside, a falling clock seems to slow, dim, and asymptotically freeze. From the inside, it's perfectly normal Tuesday, right up to the part where Tuesdays stop existing. You steal a glance at the light around the system. Photons fleeing the minidisks you admired earlier crawl away redder than they started. That's gravitational redshift. Clocks deeper and the well chime slower, so their light waves lengthen on the climb. If you could text a friend on a picnic blanket far from here, your pings would arrive late and lazy, like they got stuck in cosmic traffic. And if your friend texted back Amwa, the reply would show up almost on beat for you, but your friend's log would insist you were the one dragging your feet. Relativity, still ruining group chats since 1915. You try the thought experiment physicists pass around like a thermos of coffee. Two identical clocks, one left on a space station, one dipped close to the black hole and returned. Compare them later, and the traveler reads younger. It's the gravitational twin paradox in a tailored suit. The universe pays interest on altitude. We see this for real on Earth. GPS satellites must correct for both their speed, special relativity slows their clocks, and their altitude, general relativity speeds them up. Without daily tweaks of about 38 microseconds, your Maps app would send you confidently into a lake. Not ideal, unless you're shopping for kayaks. As the black holes twine closer, frame dragging stirs the stew. Spinning holes torque spacetime itself, and near the ergosphere, the region outside a rapidly rotating horizon, time mixes with space so intimately that just standing still becomes illegal. The only allowed rest is rotation with the hole, a cosmic moving walkway you can't step off. If you could hover there with thrusters and a ridiculous fuel budget, your wristwatch would lag compared to one lounging in deep space. You wouldn't feel sluggish, you'd feel fine, but time is petty and keeps receipts. A mainstream anchor drops into your mind. In 1919, during a solar eclipse, Arthur Eddington measured starlight deflected by the sun's gravity, a marquee test of Einstein's prediction. The bending wasn't just about space curving. It also whispered that clocks in deeper gravity tick slower. That expedition turned Einstein from theoretical whisper to global headline. Historians still argue whether the measurements were as ironclad as they were reported or if the hype outpaced the error bars, but a century of better observations has piled on the confirmation. The universe shrugs. Yes, space is bendy. Yes, time is too. Here's a quirky tidbit to tuck behind your ear. Ancient water clocks, clepsydras, kept time by dripping at a supposedly steady rate. Some designs corrected for changing pressure as water level fell with a swell in the basin. If you carried a clepsydra close to a black hole, the drip would honestly keep its rhythm. Your local physics stays loyal, while a distant observer would swear your clock had become a lazy faucet. Somewhere a Mesopotamian engineer raises an eyebrow, vindicated across 4,000 years. You wonder what now even means here. The pair's inspiral is quickening, their gravitational waves arriving with that telltale rising pitch. From the vantage of an astronomer on Earth, or whatever far-off rock boasts a detector, the chirp begins, swells, and ends in a clean snap. But you, skimming closer to the edges of their gravity wells, could watch the final orbits look like they slow and smear, each flash from a hot knot of gas stretched into longer, dimmer pulses. Two realities, both true, parceled out by where you dare to float. Light itself gets dragged into the drama. Photons passing near the holes take longer routes, the famous Shapiro delay, like spacetime saying, "Scenic route, I insist." If you were pinging a mirror on the far side of the system, you'd see the round trip time swell and shrink as the orbit evolves. It's navigation by patience, not by sight. And because the holes are moving quickly now, their Doppler shifts modulate the glow of any remaining gas. Brighter and bluer when whirling toward you, dimmer and redder when they swing away. The dance writes a clock in color. You think back to the invisible handshake and realize it's also a handshake with time. Every bit of orbital energy turned into waves is a tiny tax that time collects for letting massive things move the way they do. The closer they get, the more the tax bill balloons, the faster the seconds slip. It's why the chirp is such a giveaway. The rising frequency is time's signature scrawled across the waveform. Here's a small joke you don't say aloud because the vacuum is terrible at banter. You finally found a place where "I'm late because time ran slower" is both true and still not acceptable to your boss. Add it to your list of cosmic excuses, right next to "frame dragging ate my homework." And if someone ever asks whether you believe in fate, point them to two black holes in a decaying orbit. It's not fate, strictly speaking. It's calculus with a flair for suspense. But it feels fated when the clock itself leans in. History sidles in again, uninvited but welcome. In 1971, the Hayfel-Keating experiment flew atomic clocks on commercial airliners around the world. When they landed, the airborne clocks disagreed with ground clocks by exactly the tiny amounts relativity predicted. Not a black hole in sight, just Earth's mild gravity and some jet lag. But the point stands. Your intuition about time is adorable and wrong. Out here, the correction isn't microseconds. It's malleability you can almost taste. There's a delicate philosophical itch you can't help scratching. Does the merger finish for a distant observer, given that infalling things look frozen on the horizon? Yes, because what detectors see is generated by the strong field dance just outside the horizons and the rapid change in the spacetime shape. The ringdom, the clean, damped oscillation after the collision, gets out just fine. Locally, the horizons join quickly. Distantly, the story resolves in a handful of milliseconds. Two timelines reconcile, no paradox required, just different camera angles. Like arguing over whether a show aired at 8 when you recorded it and started at 8:30. Both are true, your popcorn doesn't care. You drift a touch closer, still safe, promise, and feel that elastic quality heighten. It's not dizziness, it's the sense that your internal metronome has learned jazz. The binary's orbital period is dropping, their spins may be processing, nudging the waveform with a gentle wobble. In the mathematics, the parameter Tc, the coalescence time, is marching toward you. In your bones, it feels like a held breath. Final joke to yourself as the stars smear. If the universe had a loading wheel, you're staring at it, except the wheel speeds up the nearer it gets to done. Cosmic progress bar. 73%, 86%, 97% done. No patch notes, no changelog, just a new spacetime with one horizon where there were two. And there you are, in the soft hum, counting seconds that refuse to be universal, whispering to a clock that only ever belonged to you. The first real hello from these two comes not from the darkness in front of you, but from a memory that doesn't belong to you at all. It belongs to 2015. You weren't there, of course, but the story has been told so many times it might as well be muscle memory for humanity's collective brain. A faint, rising chirp reached Earth, lasting less than half a second, a ripple that had traveled 1.3 billion years to arrive. It was the sound, not in air, but translated from spacetime flexing, that confirmed what physicists had been betting on for a century. Two black holes had merged. The Laser Interferometer Gravitational Wave Observatory, LIGO, had caught it. The official name was GW150914, a string of letters and numbers that looks like a password you'd never remember. But inside that bland label was the first direct detection of gravitational waves. Two stellar mass black holes, 36 and 29 times the Sun's mass, had spiraled together, merged, and left behind a single black hole of 62 solar masses. The math says 3 solar masses worth of material didn't stick around. It left as pure gravitational wave energy. You imagine it. For billions of years, those two orbited in total anonymity, in some galaxy whose light had only just reached us. They had no witnesses, no applause, just a physics problem quietly solving itself. And then, for the last fractions of a second, their gravitational waves swelled in frequency and amplitude, slicing through the cosmos until, on September 14th, they brushed through 2 quiet vacuum tubes in Washington State and Louisiana. Historians still argue whether that moment was the birth of a new astronomy, or simply the latest tool in a toolbox humanity has been filling for centuries. The quirky part: the data wasn't even spotted by a bleary-eyed grad student squinting at a screen. It was flagged automatically by algorithms and then confirmed by people. Somewhere in an office chair, someone scrolled through that strange, perfect signal and knew, in the time it takes to sip coffee, that Einstein had been right in ways even Einstein had doubted. What LIGO detected that day is exactly the kind of finale your 2 companions ahead will one day produce. The chirp encodes their mass, their spins, their distance from us. It's like an audio fingerprint, so precise that scientists can say how far away the merger happened, and roughly when in cosmic history. If the system is close enough, they can even triangulate its position in the sky, narrowing down where to point telescopes for any possible light. Not that black hole mergers promise much in the way of visible spectacle. Most are dark events, no gas to light up, no fireworks. But GW150914 had siblings. GW170817, detected 2 years later, came not from black holes but from neutron stars, and that one lit up the sky in a kilonova, producing heavy elements like gold and platinum. Even then, the gravitational wave detection was what gave astronomers the head start to catch it in action. Without the waves, they'd have been staring at the wrong patch of sky, waiting for luck to cough politely. Your 2 dancers right now aren't broadcasting a chirp loud enough for Earth to notice, not yet. But the principle is the same. Their orbit is a slow radio dial moving toward a station you can only tune into once. When they reach that frequency, the last few dozen orbits will blur into one furious crescendo, the merger in all its curved spacetime glory, followed by the ringdom as the new black hole settles into a quieter, steadier shape. And that ringdom, the aftershock, has a tone all its own, set by the final black hole's mass and spin. It's like the instrument swap at the end of a song. You know the set, over, but you hang around because you like how the last notes fade. LIGO caught that in GW150914 too, though the faintness meant it was more like overhearing the last chord through a thin wall. You think about the sheer delicacy of this kind of detection. Earth is buzzing with noise, traffic, earthquakes, ocean waves, even wind rattling the detector's buildings. The quiet needed to hear a gravitational wave means filtering out all that chaos until you're left with a signal smaller than the width of a proton. And still, the moment that chirp passes, it's undeniable. Somewhere in the memory of GW150914, you find a new appreciation for your current vantage point. You're floating at the scene of the crime before it happens, in the long prelude that no one on Earth could detect even if they wanted to. Your presence here is the universe's spoiler warning. This one will merge. It might take thousands or millions of years, but when it does, someone, something, might hear the same quick chirp you're already imagining. The best part, that first detection in 2015 wasn't a fluke. Since then, LIGO, Virgo, and KAGRA have recorded dozens of black hole mergers, some so frequent they almost feel routine. But you know better than to call them that. Each one is a one-time event, a unique pattern in the ripples, carrying information that can't be replayed. You get one listen. After that, the song is over, the waves gone forever into the dark. Your two dancers may be the modest, stellar mass kind, but not all black hole pairings are created equal. Out here, the universe loves variety, like a cosmic matchmaking service with an endless database, sometimes pairing too small, sometimes too massive, sometimes a David and a Goliath. And somewhere far beyond your current vantage, black holes merge on scales so huge that even light takes minutes to cross their horizons. Supermassive black holes, for example, make your pair look like toy marbles. These are the gravitational tyrants at the hearts of galaxies, millions to billions of solar masses each. Our own Milky Way's central black hole, Sagittarius A, is a relatively polite 4 million solar masses, but others, like the one in galaxy ton 618, tip the scale at an estimated 66 billion solar masses. If two galaxies happen to drift into each other's arms, as galaxies often do, their central supermassives begin their own, far grander merger dance. The process is the same physics you're watching now, just with deeper gravity wells and far more drawn-out timelines. Historians still argue whether the giant radio lobes cataloged in the mid-20th century were the first indirect hints of supermassive black holes colliding, their jets marking where galactic centers had merged and stirred up their surroundings. Some point to quasars, blindingly bright active galactic nuclei, as another piece of the puzzle, fueled by torrents of gas feeding these monsters before and during their union. The quirky twist is that size changes not just the scale, but the soundtrack. Stellar mass black hole mergers like the one you're watching emit gravitational waves in frequencies high enough for ground-based detectors like LIGO and Virgo to catch. Supermassive mergers sing in bass notes far below human hearing, periods measured in hours or days instead of milliseconds. Ground-based detectors can't hear those. The arms would have to be millions of kilometers long. That's where space missions like LISA, Laser Interferometer Space Antenna, will come in, using 3 spacecraft trailing Earth to form a detector vast enough to catch those slow spacetime undulations. You imagine a future where both kinds of detectors, space and ground-based, work together, like bass and treble in the same piece of music, giving a complete symphony of the gravitational universe. Closer to home, mergers can also involve mismatched partners. Picture a black hole swallowing a neutron star. These are the cosmic mixed doubles matches, and when they happen, the gravitational waves carry a telltale imprint of the neutron star's tidal stretching and eventual consumption. In some cases, the neutron star might be shredded outside the event horizon, spilling hot debris that could light up the sky in a short gamma-ray burst, a flash visible across galaxies. In others, it disappears whole, the only record of its passing etched in spacetime ripples. For pure black hole pairs, the mass ratio matters. Equal mass mergers produce the strongest and most symmetric waves, a clean crescendo into ringdom. Unequal pairs, say 30 solar masses merging with 10, produce more lopsided signals. The smaller one gets whipped around faster, and the gravitational waves have a slight asymmetry, a subtle off-balance sway encoded in the chirp. Astrophysicists read those sways like a detective scanning handwriting for personality quirks. Your two companions now are likely somewhere between 5 and 50 solar masses each. That's the sweet spot for LIGO's hearing range, and for black holes born from massive star collapse. They're too small to affect their galaxy in any dramatic way, No stars being slingshotted thousands of light years, no galaxy-spanning jets, but in their final seconds, they'll still outshine the rest of the observable universe in gravitational wave power. Thinking about that scale difference makes you glance out into the wider dark. Somewhere, supermassive pairs are doing this too. Their orbits so wide they take millions of years just to make a single lap. Somewhere else, intermediate mass black holes, hundreds to thousands of solar masses, are colliding in globular clusters, perhaps built from smaller mergers. And then there's the wild card: primordial black holes, hypothetical relics from the Big Bang, possibly with masses ranging from asteroids to mountains, colliding silently in the deep past. The diversity is dizzying, but the underlying story is the same. Mass curves spacetime, orbiting masses send out ripples, and if you wait long enough, two become one. Whether it's your pair tonight or a pair that could swallow our sun without noticing, the cosmic rules don't bend. It's tempting to anthropomorphize, to imagine the smaller black holes looking up to the bigger ones like apprentices, or the supermassive pairs treating your stellar mass duo like overenthusiastic kids at a wedding dance. But the truth is both more ruthless and more beautiful. Mass and energy follow the equations, and the dance is dictated by geometry itself. You hang there for a moment, absorbing the idea that not all mergers are equal doesn't just mean size. It means timeline, frequency, visibility, aftermath. Somewhere, a supermassive merger is shaping the future of its galaxy. Somewhere else, a small one is quietly sending a ripple that no one will notice for eons. And here in front of you, a modest pair is marking time until their turn in the cosmic spotlight. A performance they'll give exactly once, never to be repeated. If you could somehow plug your consciousness into the fabric of spacetime right now, the two black holes ahead would already be humming to you, not in light or heat, but in frequency. The cosmic chirp is what scientists call it, though in reality it's a rise in the pitch of gravitational waves as the pair spirals inward. It's the closest the universe gets to leaning over and saying, "Listen, it's about to happen." Right now, the chirp is far too low for human detectors on Earth to hear. The orbital period is still hours long, so the waves, frequency is down in the nanohertz to millihertz range, miles below LIGO's sweet spot. But given enough time, orbital energy will bleed away into those ripples, and the pair will move faster and faster, the waves climbing steadily toward that detectable range. In their last minutes, the pitch will soar from tens of hertz to hundreds, a perfect glissando written in spacetime. The first time humans heard such a chirp was in that now famous 2015 event, GW150914. The recording lasts just 0.2 seconds, starting as a faint thrum, rising sharply, then cutting off. That's not just drama, it's the physics of the merger. As the black holes orbit faster, they draw closer. The gravitational waves gain frequency and amplitude, and then, the collision wipes the signal clean. The beauty is in the math. The chirp's shape comes from how the orbital radius shrinks with time. In relativity, the separation RR falls roughly as Tc minus T 1/4, TCT 1/4 near the end, where TCTC is the merger moment. The frequency is tied to RR by Kepler's laws and relativity's corrections, so it rises in a way that's incredibly consistent. You can listen to the waveform and, without seeing a single photon, deduce the masses, spins, and even some hints about the orbit's history. Quirky fact: physicists sometimes speed up or slow down chirps to shift them into the human hearing range. That's why, in outreach talks, you can actually hear a black hole merger through speakers. The version they play is like translating a whale song into a flute solo. It's the same melody, just in a register your ears can handle. As the chirp climbs, the gravitational waves also carry away angular momentum, meaning the orbit becomes more circular. Even if the black holes started with an eccentric path, elongated and lopsided, the emission of waves smooths it into a nearly perfect spiral by the time they're in LIGO's range. Historians still argue whether some captured pairs might keep a little eccentricity into the final seconds, a potential signature of chaotic formation in star clusters. It's the astrophysical equivalent of spotting a dancer who refuses to stick to the choreography. Your pair now is probably too far apart for any detector to pick them up, but the principle is alive in every spin of their orbit. If you could wait here through the millennia, you'd feel the hum rise imperceptibly at first, then faster and faster, until each orbit zipped by in less time than it takes to blink. The waves would go from bass so low you'd need a detector the size of a galaxy, to treble so sharp it could be compressed into a brief, bright note in the LIGO archives. A mainstream anchor in your thoughts. When scientists sift through data looking for these chirps, they use a technique called matched filtering, comparing the noisy incoming signal to a bank of pre-computed templates. Each template is a chirp waveform generated by running Einstein's equations forward for hypothetical pairs of masses and spins. When the data lines up with one of these templates, it's like finding the right puzzle piece. The match spikes, and a potential detection is flagged. Without this, the signals would be lost in the background noise of Earth itself. And here's a quirky add-on. The sound of the chirp is more than just educational fun. The human brain is oddly good at pattern recognition in audio, so some researchers actually listen to sped-up data streams as an informal check. It's not how detections are confirmed, but if you've been working with these signals long enough, a sudden whoop in the static can make you lean closer to your desk before you even look at the plots. You drift a little nearer to your two black holes, imagining their future waveform. At the moment, their chirp would be so slow and deep it's more like a tectonic groan, one cycle every few hours. Over millions of years, that groan will quicken to minutes, then seconds, then fractions of seconds, until their last lap comes and goes in less time than a camera shutter click. When they do, the chirp they send will race away in all directions. Somewhere, maybe in the dusty living room of a future LIGO-3 operator, a monitor will spike. Maybe that operator will yawn, sip coffee, and smile quietly, knowing they've just caught the death and birth of a black hole system millions of years after it happened. And they'll know it instantly, not because of what they saw, but because they heard spacetime sing. Your gaze drifts from the tight, intimate orbit in front of you to the broad sweep of the cosmos, and suddenly the scale of this dance feels almost parochial. Stellar mass black holes can find each other in a few ways, but for the biggest, slowest, and most dramatic unions, you have to zoom out to the grand ballroom. Entire galaxies colliding. Galaxies are social creatures. They wander through the cosmic web, tugged by the gravity of their neighbors, and sometimes they can't resist each other's pull. The Milky Way, for example, is on a slow-motion collision course with Andromeda, scheduled for about 4 billion years from now. When galaxies meet, their stars rarely collide directly. Space is that empty. But their gas clouds smash together, trigger waves of new star formation, and their central supermassive black holes start the slow gravitational tango that will eventually end in a merger. The first step in galactic speed dating is simply getting the central black holes into the same gravitational arena. At the moment of first galactic contact, the two giants may be hundreds of thousands of light years apart, orbiting in the messy gravitational field of the merged galaxy. Over millions of years, they spiral inward thanks to dynamical friction, a process where their motion through the surrounding sea of stars and dark matter creates a gravitational wake, robbing them of momentum. A mainstream anchor drops into your mind. In 2002, the Hubble Space Telescope imaged NGC 6240, a galaxy in the throes of a merger. At its heart, astronomers spotted not one but two supermassive black holes about 3,000 light years apart. It was one of the first clear photographic hints that galaxy mergers carry double trouble in their cores. Historians still argue whether earlier radio observations had already revealed such pairs and simply been overlooked in the shuffle of data. You notice something quirky about this process. It's so slow that the most violent part of a galaxy collision, The wild bursts of star formation and the twisting tidal tails fades long before the black holes finally meet. By the time the central monsters are close enough for gravitational waves to take over, the galaxy might look perfectly calm to an outsider, its wild youth hidden in the fossil record of its stars. Back in your own patch of space, you picture what's happening inside those merging galaxies during the approach. Gas can be funneled inward by the changing gravitational potential, feeding both black holes and turning them into quasars for a time. Bright, active nuclei blasting jets and radiation into space. If both are active at once, the system becomes a rare dual quasar. Astronomers hunt for these, not just for the novelty, but because they're snapshots of black holes before the final pairing. The speed in galactic speed dating is a joke, really, millions to billions of years of careful choreography. And yet, when two central black holes finally get close enough, the pace changes. Just like your smaller pair here, they begin to lose energy through gravitational waves, the orbit tightening from light years to parsecs to fractions of a parsec. There's a catch, though, the dreaded final parsec problem. Simulations suggest that once the orbit is small enough that dynamical friction no longer works efficiently, the black holes can stall. Without some other mechanism, gas drag, interactions with passing stars, or even the intrusion of a third black hole, they might never get close enough for gravitational waves to do the rest. In reality, the universe seems to find ways around this, but exactly how often and by which methods is still a lively debate in astrophysics departments. You think of this as the cosmic equivalent of a couple stuck in the "we should move in together" phase for a suspiciously long time. Eventually, something, an eccentric relative, a sudden opportunity, forces the decision. Out here, it might be a star wandering too close, flinging some angular momentum out of the system and letting the black holes close the gap. Quirky tidbit: the largest black hole merger humanity might one day witness could come from two supermassives in a galaxy called OJ 287. It's a suspected binary system where one black hole is about 18 billion solar masses and the other is a mere 150 million. The smaller one's orbit brings it crashing through the accretion disk of the big one twice every 12 years, producing predictable flares in visible light. If they eventually merge, the gravitational waves would be so powerful that even Lisa might blush. You bring your attention back to the present. The two black holes in front of you aren't supermassive, and they didn't need galactic mergers to find each other. But the principle is the same. Gravity has brought them into the same space, and their interaction will only grow tighter. In the grand scheme, they're just one couple among billions across the observable universe, each somewhere along that same story arc. First encounter, slow approach, locked orbit, and finally merger. It's humbling, really. From stellar mass pairs born in a single star-forming region to supermassive titans drawn together by galactic reshaping, the geometry of spacetime applies without prejudice. And whether the prelude lasts millions of years or billions, the ending, the moment of one becoming one, is over in the blink of an eye. For all this talk of inevitability, the truth is, black holes don't always get to the altar. Sometimes the dance just stalls. It's a problem so persistent it has its own nickname, the final parsec problem. Imagine our two partners closing the gap from light years to mere parsecs. That's already an impressive feat, like bringing two cruise ships into formation in the middle of a storm. But then within that last parsec, the very mechanism that's been pulling them together, dynamical friction, loses its teeth. Dynamical friction works best when there's a rich crowd of stars, gas clouds, or dark matter particles for the black holes to plow through. Every pass tugs on those objects gravitationally, creating a wake that saps momentum from the black hole and slows it down. But once the binary is tight enough, the surrounding crowd thins out. Fewer stars wander into the danger zone, and the wakes get too faint to matter. Without that drag, the orbit can linger for billions of years. Historians still argue whether we've actually seen stalled black hole binaries, or whether it's just a theoretical nuisance. Some observations of galaxies with dual active nuclei suggest the pairs are still too far apart for gravitational waves to take over. But whether they'll ever shrink further depends on factors we can't easily measure, like how much cold gas is hanging around, or how often other stars dive in to stir the pot. Quirky twist: nature sometimes cheats. A passing third black hole, born from another galaxy collision, can blunder into the system. Three-body interactions are notoriously chaotic. One black hole can get flung out entirely, and the remaining pair can suddenly find themselves in a much tighter orbit, close enough for gravitational waves to finish the job. It's the gravitational version of a surprise plot twist, where one character leaves the story entirely, but somehow pushes the other two into a romantic finale. There's also the gas option. If enough interstellar gas falls inward, it can form a circumbinary disk around the black holes. Viscous torques in that disk can transfer angular momentum outward, tightening the orbit. In simulations, this can push the pair right past the final parsec into the gravitational wave regime. Whether that happens often enough in real galaxies is still up for debate. Another favorite topic at astronomy conferences, where someone inevitably gestures at a messy simulation on the big screen and says, "See, it can work." You glance at your own two companions ahead. They're stellar mass black holes, so their version of the final parsec problem isn't quite the same. Stars and gas aren't needed to shrink their orbit. Gravitational waves can handle the whole job for small pairs, given enough time. But they do face their own hurdles. For example, if they were born far apart in a triple star system, they might never get close enough unless the third star's gravity periodically nudges their orbits into more eccentric shapes. Those eccentric orbits lose energy faster through waves, pulling the pair together much more quickly. Mainstream anchor for your mental scrapbook. The Hulse-Taylor binary from 1974 wasn't a black hole pair but two neutron stars. Its orbital period was shrinking exactly as predicted by gravitational wave emission. No final parsec stall, no need for a third body. That system is still spiraling toward its merger, due in about 300 million years. If it were a black hole pair with similar mass and separation, the same math would apply. And here's the little observational irony. The final parsec problem may be one reason why we haven't already detected gravitational waves from supermassive black hole mergers with pulsar timing arrays. Those arrays, which measure tiny shifts in the timing of millisecond pulsars across the galaxy, are tuned to hear the low-frequency hum of such giants. If many supermassive pairs are stuck just outside the gravitational wave, loud zone, the hum would be fainter than expected. Recent hints from nanograv suggest the hum might finally be emerging, but whether it's loud enough to confirm the theory is still in the air. Your two black holes up close, though, they're not stuck. Theirs is a clean gravitational wave, driven in spiral, no final parsec stall in sight. That's the joy of the smaller scale. The math is more straightforward, the physics less dependent on messy galactic environments. All they need is time, and spacetime itself is willing to give it while taking it away. You drift a little closer, catching the faintest flicker of gravitational lensing as one passes behind the other from your viewpoint. It's a tiny preview of what will one day be a furious, last-second blur. You can't help but feel a little smug on their behalf. These two won't have to endure awkward millennia of orbital stagnation. Their story will reach its end without a cosmic counselor or a gas disk intervention. Still, the final parsec problem is a reminder that not all black hole romances are neat and tidy. Some pairs linger forever, locked in a gravitational engagement that never leads to a wedding. Others get an unexpected push, or a messy three-body breakup, and rush to the altar. And some, like the ones before you, are simply counting down the clock, with no roadblocks left between them and the moment spacetime itself will shudder. Not every merger makes headlines, or even makes it into our detectors. Out here in the cosmic ocean, some black hole collisions are simply too faint, too far, or too awkwardly pitched for us to notice. They still happen, quietly, relentlessly, but they vanish into the background noise of the universe like whispers in a hurricane. The most obvious reason we miss them is distance. Even a strong gravitational wave weakens as it spreads across space. By the time a far-flung merger's ripples reach Earth, their stretching and squeezing of spacetime might be so tiny that even LIGO's laser arms can't feel it. That's not a failure of physics. It's just reality's way of saying, you can't be everywhere at once. A black hole merger 10 billion light-years away could be roaring in its own corner of spacetime right now, and our instruments would register nothing more than static. Then there's frequency. LIGO, Virgo, and KAGRA are sensitive to a certain band, roughly tens to thousands of hertz. Stellar mass black holes in their final seconds fit neatly into that range, but supermassive pairs sing in frequencies so low that our ground-based detectors are deaf to them. We need space missions like LISA for that, and until LISA launches, those slow, deep rumbles remain out of reach. Pulsar timing arrays are already trying, using the galaxy itself as a detector, but those searches require decades of patient listening. Historians still argue whether some odd blips in older data sets, once dismissed as noise, were actually distant, faint black hole mergers we weren't equipped to confirm. It's the kind of hindsight that keeps graduate students combing through archives on the off chance that a Nobel Prize is hiding in a dusty file from 1998. There's also the matter of orientation. Gravitational waves radiate in patterns, louder in some directions, fainter in others. If a merger happens to beam more energy away from our line of sight, the signal might be just a hair too weak to stand out above the background hum. It's like being in the wrong section of a stadium and missing half the sound of the band. And then there are the true ghosts, mergers without any accompanying light. Black hole collisions are the rule here. Without gas or dust to heat up, they leave no electromagnetic fingerprint, no flash for telescopes to chase. Neutron star mergers at least have the decency to throw some visible fireworks, but black holes alone, they just blend back into the dark. Quirky tidbit: astronomers have speculated about black holes merging inside dense stellar clusters, or even in the accretion disks of supermassive black holes. These environments could muffle or distort the gravitational waves, and if the surroundings are noisy enough, filled with other gravitational interactions, it might be like trying to pick out a single violin in a subway station full of buskers. Even when we do catch a faint signal, it can be borderline. The detection pipelines are built to flag candidates that match theoretical waveforms, but very weak ones might hover below the threshold. Some end up in sub-threshold catalogs, lists of maybe mergers that can't be confirmed without future improvements in sensitivity. In a way, they're like the uncredited extras of the cosmic drama, there, but without enough lines to get their name in the credits. Your two companions tonight are lucky in that regard. They're close enough, and when they merge, they'll shout loudly enough for modern detectors to hear. But somewhere, perhaps on the far side of the observable universe, another pair is already in its final orbits, sending waves so faint that no one, no human, no alien, no machine, will ever know. The ripples will simply pass by, warping spacetime by less than the width of an atomic nucleus, unrecorded and uncelebrated. Mainstream anchor in your mental scrapbook. The LIGO, Virgo catalogs list over 90 confirmed gravitational wave events so far, but statistical models suggest thousands happen every year in the volume of space we could, in theory, detect. That means we're currently missing the vast majority, hearing only the loudest, closest, or best-oriented ones. The rest dissolve into what scientists call the stochastic gravitational wave background, a faint, random hiss made from countless undetected mergers overlapping in time. You glance back at your pair and think of them as future celebrities in a galaxy where most of their peers will never get the spotlight. They'll get their moment, an unmistakable chirp, and then fade into anonymity again as a single, larger black hole. But for everyone like them, dozens more will live and die in gravitational silence from our point of view. And maybe that's the point. The universe doesn't stage its events for observers. It just keeps running the same physics over and over, whether or not anyone is listening. The quiet ones are no less real. They just happen to be private performances in a theater too big for us to fill. Every so often, the cosmic waltz gets gate-crashed. Not just by one intruder, but sometimes by two, forming a party of 3 black holes in the same gravitational neighborhood. And unlike human dance floors, where a third wheel just awkwardly sways near the punch bowl, here the arrival of a third black hole can turn the choreography chaotic. Picture your 2 partners, locked in their slow spiral, minding their own orbital business. Now imagine a newcomer barreling in, maybe the leftover supermassive black hole from another galactic merger, or a stellar mass wanderer kicked in from a nearby cluster. 3-body systems are famously unstable. Gravity, when it's working in threes, prefers drama. Often one body gets flung away entirely, and the other 2 end up in a tighter, more eccentric orbit. Historians still argue whether some of the closest black hole pairs we've detected could only have formed thanks to this kind of chaotic matchmaking. The math supports it. A random close pass can shrink the separation enough that gravitational waves take over almost immediately. The downside for the ejected third wheel: it can get launched at speeds so high it leaves its galaxy forever, becoming a lonely wanderer through intergalactic space. Quirky twist: in a few rare cases, the third body doesn't get kicked out right away. Instead, all 3 engage in a kind of gravitational juggling act, swapping partners repeatedly before the system finally decides who stays bound to whom. These exchanges can last thousands of orbits, each pass twisting the spacetime geometry and spraying gravitational waves in irregular bursts, far messier than the clean chirp of a 2-body merger. From a detection standpoint, triple black hole encounters are tantalizing but tricky. The gravitational waveforms they produce aren't neat and predictable. They're chaotic, with sudden spikes and long lulls. LIGO and Virgo's template banks are built mostly for tidy, binary mergers, so anything too unruly risks slipping past unnoticed. That's why some researchers are developing new search methods aimed specifically at catching the signatures of triples, a kind of cosmic eavesdropping on fights in the dark. Your pair ahead probably won't suffer this fate. They're deep enough into their isolated inspiral that a third interloper would have to be astonishingly unlucky, or lucky, depending on perspective, to pass close enough to interfere. Still, you imagine it, a rogue black hole swooping in, curving spacetime in an unfamiliar way, warping their neat orbit into something jagged and eccentric. The waves would turn erratic, like a song that can't keep a beat, before settling into a new rhythm as one partner gets hurled into the dark. Mainstream anchor for your memory book: the galaxy NGC 6240, the same one that gave us 2 supermassive black holes in close proximity, was later revealed to have 3 at its center. Observations in 2017 showed a triple system, with 2 already close to merging and the third orbiting not far away. It's one of the clearest examples yet of how galactic collisions can lead to a gravitational ménage à trois. Astronomers think the central region's crowded history might help solve the final parsec problem there by giving the central pair a constant supply of stars, and possibly that third black hole to shake things up. Even stranger are the simulations showing that triple systems might occasionally produce near-simultaneous mergers. Imagine 2 black holes collide, sending out a burst of gravitational waves, while a third, now in a new orbit, spirals inward and merges just months or years later. From Earth, we might detect 2 chirps from the same patch of sky in quick succession, a cosmic double feature. Quirky fact: a black hole flung from a triple encounter isn't necessarily doomed to eternal loneliness. If it speeds through a dense star cluster, it could capture another companion and start the dance again, like a serial romantic forever finding new partners to spiral toward. Gravity, it seems, doesn't mind repeat customers. You look back at your own quiet duet, grateful for their simplicity. No chaotic third parties, no erratic bursts, just the slow, steady tightening of a system destined for one big finale. Still, somewhere out there tonight, a triple system is making a mess of spacetime, flinging one member into the cosmic wilderness while the other two embrace in a doomed, tighter orbit. The universe has a flair for both order and chaos, and it never seems to get tired of mixing them together. From where you float, the two black holes ahead look quiet. No jets, no flares, no glowing fireworks. Just two invisible pits in spacetime getting closer. And yet, the merger they're headed toward will shake their corner of the universe in ways that go far beyond the ripples of gravitational waves. Even without a single photon of visible light, a black hole collision can be a kind of cosmic fireworks show, if you know what to look for. Start with the stars. If the black holes are part of a dense star cluster or a galactic nucleus, their changing gravitational field can fling nearby stars onto new orbits. Some get kicked inward, some outward, and some accelerated so violently they leave the galaxy entirely. These hypervelocity stars shoot through intergalactic space like glowing bullets, fast, rare, and carrying the signature of a gravitational sling. Historians still argue whether some of the rogue stars cataloged in our own Milky Way are leftovers from ancient black hole mergers in the galactic core. Then there's the matter of gas. If a binary black hole system lives inside a cloud of interstellar gas, or in a disk of material around a supermassive black hole, its merger can stir that gas violently. Shockwaves ripple through it, heating it up, changing its chemistry, and sometimes triggering bursts of star formation. Astronomers call these merger-induced starbursts, and they can light up a galaxy for tens of millions of years after the actual black hole collision. The light we see from such a starburst isn't the fireworks itself. It's the glitter that settles in after the fuse is gone. Quirky twist. Simulations suggest that a big black hole merger can even kick the remnant black hole hard enough to shove it off-center in its host galaxy. This gravitational recoil comes from gravitational waves leaving the system unevenly. If the waves are stronger in one direction, the merged black hole gets a recoil kick in the opposite direction. In extreme cases, it could be thrown right out of the galaxy, taking its surrounding stars and gas with it. Imagine a sparkler that, instead of fading, runs off into the dark with half the tablecloth. Even when no light escapes, the gravitational waves themselves carry colossal amounts of energy, briefly more than the combined light of all stars in the observable universe. That power doesn't heat or illuminate in the way we're used to, but it does reshape the cosmic environment. A passing wave can subtly alter the orbits of stars and even slightly distort the shape of entire galaxies. You wouldn't see it happen, but if you could freeze time and measure every position, the geometry would tell the tale. Mainstream anchor for your mental scrapbook. In 2019, a gravitational wave event called GW190521 was detected. It came from the merger of two unusually massive stellar black holes, 85 and 66 solar masses, and the result was a black hole 142 times the mass of the Sun. The energy radiated away in gravitational waves was equivalent to about 8 solar masses. No visible light was confirmed, but later, astronomers spotted a flare from an active galactic nucleus in roughly the same spot, possibly from the merged black hole plowing through surrounding gas. The jury's still out, but it's a rare possible glimpse of a normally invisible kind of fireworks. Here's a quirk you can't stop thinking about. In the early universe, before galaxies had fully settled, black hole mergers may have been even more influential. By shaking up the gas and triggering rapid star formation, they could have helped sculpt the first large-scale structures of the cosmos. In that sense, every galaxy's current shape might be, in part, the aftermath of countless dark fireworks no one ever saw. Your own two dancers don't have much gas left around them. When they finally merge, it will be a clean, silent union as far as light is concerned. But their gravitational waves will still race outward, maybe passing through a nearby star cluster and tweaking orbits there. The ripple effect is literal. One moment here, felt across light years, influencing the dance of things that will never know the cause. You hover a moment longer, appreciating the irony. These fireworks without light are in some ways grander than the most dazzling supernova. They involve more raw energy, affect a larger swath of space, and last far longer in their consequences. They just happen to be invisible to human eyes, requiring instruments, patience, and a bit of stubborn curiosity to notice. Somewhere out there, in a galaxy you'll never see, another pair of black holes has already merged, sending waves that have been traveling for billions of years. They may have rearranged the stars in their neighborhood, lit a few with new fusion, or even kicked their remnant into exile. No one was there to see it. And yet, the universe remembers, in its geometry, in its patterns, and in the quiet paths of the stars it nudged along the way. The two black holes ahead are on a collision course that will send gravitational waves rippling across the cosmos. But here's a question that nags at the human part of your brain. Aside from the waves themselves, do these events make anything? When two black holes merge, are they just cosmic paper shredders, or could they actually forge something new? The straightforward answer is, usually no. Black holes are notoriously stingy about giving matter back once it's inside the event horizon. For most mergers, especially those without much surrounding gas, the result is simply a bigger black hole plus gravitational waves. No light, no debris, no shiny leftovers. But that's not the whole story. Under the right circumstances, if there's enough material nearby, or if the merger involves other kinds of compact objects, the results can get a lot more creative. Take neutron stars, for example. When two of those collide, the impact can forge heavy elements like gold, platinum, and uranium in a process called R-process nucleosynthesis. In 2017, GW170817 proved it by giving astronomers a kilonova to study, a brilliant explosion that scattered freshly minted heavy metals into space. Historians still argue whether any black hole mergers could do something similar. The challenge is, pure black hole mergers don't have free matter to throw around, unless they happen inside an environment rich with gas or a pre-existing accretion disk. In that case, the merger might jolt and compress surrounding matter enough to trigger nuclear reactions or shockwaves that synthesize new elements. Quirky twist. One speculative idea says that if two black holes merge inside a dense, magnetized disk around a supermassive black hole, the collision could drive a relativistic jet. That jet could, in theory, create conditions for particle acceleration, and possibly even for rare nuclear processes. This isn't mainstream consensus. It's more of a cosmic what if that keeps theorists entertained during long conference coffee breaks. There's also the mystery of electromagnetic counterparts. While most black hole mergers are dark, some have produced candidate light signals. The aforementioned GW190521 may have been one, possibly a flare from the merged black hole smashing through a gas disk. If true, that flare could have involved enough heating and turbulence to alter the chemical makeup of its surroundings. Nothing on the scale of a neutron star merger's metal factory, but still a detectable nudge to the local environment. Mainstream anchor for your notebook. The periodic table's heaviest naturally occurring elements, gold, platinum, uranium, are now widely believed to come mostly from neutron star mergers. But some models leave room for a small contribution from exotic black hole-related events. If even a fraction of a percent of mergers happen under the right messy conditions, they could seed galaxies with trace amounts of rare isotopes over billions of years. You drift closer to your pair, picturing their merger moment. In this empty patch of space, there's almost nothing for them to affect. No gas clouds to compress, no debris to launch. When they unite, their gravitational waves will be their sole legacy. But imagine transplanting them into a busier neighborhood, say, a star-forming region thick with dust. The collision might shock that dust into collapsing into new stars or planets. No alchemy in the literal sense, but still a case of something new being born from the violence. There's another fringe idea that tugs at your thoughts: Could certain mergers create primordial-like black holes, small enough to evaporate via Hawking radiation within the current age of the universe? If that happened, the final stages of their evaporation would release high-energy particles and gamma rays, tiny fireworks marking the end of an object that began as the child of two larger ones. Mainstream astrophysics treats this as unlikely, but it's not ruled out entirely for some speculative mass ranges. Quirky fact to file away. In some galaxy simulations, a big black hole merger changes the gas dynamics enough to flip the rotation of an entire circumnuclear disk. That means stars forming afterward would orbit in the opposite direction to the older stars, a lasting scar in the galactic architecture, like a swirl in the cream that never stirs away. You look at the pair again and think, maybe they're not creators in the traditional sense. They're not forging gold or birthing new worlds here, but they're part of a chain of cause and effect stretching across time and space. Their waves might jostle something a billion light years away, just enough to tip a cloud into collapse, or knock a solitary star into a new orbit, or slightly warm the skin of a future planet. Creation, in their case, isn't about making something from scratch, it's about nudging the dominoes. And maybe that's enough. Not every kind of making has to leave something shiny in your hand. Sometimes it's enough to alter the trajectory of the next chapter, even if the change is subtle, invisible, and written in spacetime instead of starlight. By now, you've come to expect the universe to behave. Well, behave in the way a cat does, predictably unpredictable. But there's a corner of astrophysics that wonders if black hole mergers might sometimes break the rules altogether. Not in a messy, physics is wrong way, but in a physics might be bigger than we thought way. That's where the exotic possibilities live. The mainstream script says that when two black holes merge, you get a bigger black hole and a shower of gravitational waves, full stop. But what if, under the right circumstances, the merger leaves behind something stranger? Some theorists suggest that if the singularities inside black holes are replaced by some yet unknown quantum object, say, a Planck star or a gravistar, the collision might not just swallow everything cleanly. Instead, it could produce a burst of radiation or even eject exotic matter. Historians still argue whether such speculation is genius or just mathematical doodling with no observational teeth. One favorite fringe idea: mergers as gateways to wormholes. If black holes can somehow connect to other regions of spacetime, either elsewhere in our universe or to other universes entirely, then a merger might momentarily ring in a way that reflects that hidden geometry. The aftermath could look almost like a normal ringtone, but with faint echoes repeating milliseconds later, like sound bouncing in a canyon. A few gravitational wave detections have been scoured for such echoes. So far, no solid evidence, but the hunt is far from over. Quirky twist. Another speculative branch asks whether black holes might occasionally merge into something that's not a black hole at all, but a long-lived boson star, a compact object made of hypothetical ultralight particles. In this scenario, the merger's gravitational waves would slowly drift away from the predictions for a normal black hole, revealing the imposter. No one has spotted such a deviation yet, but it's the sort of thing future detectors might catch if the universe is feeling generous. And then there's the question of dark matter. If some forms of dark matter can clump inside or around black holes, their mergers could release not only gravitational waves, but also streams of dark matter particles. We wouldn't see them directly, but they might leave fingerprints in how the final black hole spins or how much mass is missing in the final accounting. A small cadre of physicists is already sketching what those signatures would look like in the data. Mainstream anchor for your mental shelf. In 2020, researchers announced that LIGO and Virgo's catalog included mergers producing black holes in the so-called mass gap, a range between about 50 and 120 solar masses where stellar collapse shouldn't normally produce them. GW190521 was one of these. One explanation is that such a black hole formed from an earlier merger, making it a hierarchical black hole. But some have speculated it could hint at something more exotic, like a primordial black hole left over from the early universe. Or, if you're feeling wild, a black hole born from new physics entirely. There's also the playful notion that black hole mergers might let us test quantum gravity, the still unfinished theory marrying relativity and quantum mechanics. If horizons have quantum hair, tiny deviations from the smooth, featureless surface predicted by classical theory, the ringed-on phase might carry those imprints. Detecting them would be like finding brushstrokes on what we thought was a perfectly smooth sculpture. Quirky fact: some models suggest that if two charged black holes were to merge, extremely rare but not impossible, the electromagnetic field could briefly produce pair cascades of particles, lighting up the surroundings in a flash of gamma rays. The odds are slim, but the thought is delightful. Black holes throwing one tiny visible tantrum before going back to invisibility. You glance at your own binary pair and try for a moment to see them as more than just points of mass. What if, inside those horizons, the singularities aren't real infinities but compressed quantum objects? What if, when they collide, the very shape of spacetime hiccups in a way we haven't learned to recognize yet? The gravitational wave chirp you'd hear might carry tiny features, a stutter here, an unexpected overnote there, clues that something exotic happened. Most likely, your two will follow the standard script. The final black hole will be a perfect example of the no-hair theorem, bald and beautiful in the way only general relativity can predict. But in a universe this large, with this many collisions somewhere sometime, there might be one that does something unexpected. Maybe we'll detect it, maybe we won't. Either way, the possibility keeps people staring at waveforms late into the night, chasing faint, impossible dreams. And that's the charm of these exotic possibilities. They remind you that for all we've learned, the next surprise could already be on its way, wrapped inside a ripple we just haven't heard yet. The two black holes you've been shadowing are destined to become one. But the moment they do, something remarkable happens. Their union gives birth to a single, larger black hole with a spin. Not just a casual twirl, but a rotational speed that can approach the speed of light at the event horizon. This after-party spin is one of the merger's most telling fingerprints. Spin in black holes isn't just an aesthetic detail, it shapes everything around them. A rotating black hole drags spacetime with it, a phenomenon called frame dragging. Near the event horizon, this effect becomes so extreme that all matter and even light are compelled to co-rotate with the black hole. The faster the spin, the stronger the drag. Mainstream anchor to store away. In the 1970s, physicists Roy Kerr and Ezra Newman worked out the exact solutions to Einstein's equations for rotating black holes, leading to what's now called the Kerr metric. Every black hole we know of can be described by just three properties: mass, spin, and charge. But in nature, charge is negligible, so spin becomes the second key descriptor after mass. Quirky twist: if a black hole spins fast enough, near the theoretical maximum, it can actually make it easier for matter to escape from its surroundings. Through a process called the Penrose process, particles entering the ergosphere, the region just outside the event horizon where frame dragging is unavoidable, can, in principle, steal some of the black hole's rotational energy. In astrophysical settings, this is one way powerful relativistic jets might be launched. When two black holes merge, the spin of the remnant depends on the spins of the original pair and the orientation of those spins relative to the orbit. If both were spinning in the same direction as their orbit, the final black hole could end up with a dizzying, high spin parameter, close to the limit allowed by relativity. But if they were spinning in opposite directions, or tilted at awkward angles, the spins can partially cancel, leaving the remnant slower. You picture your two companions now. Maybe they're aligned like synchronized swimmers, about to make a seamless dive. Or maybe their spins are messy, each tilted in a different direction, ensuring the final result is a more complicated blend. The gravitational waves in their final seconds will carry hints of this spin dance, letting future astronomers reconstruct the orientation puzzle without ever seeing the black holes themselves. Here's a quirky fact. A maximally spinning black hole could, in theory, store as much as 29% of its total mass energy in rotational energy. That's an absurdly high battery compared to anything we can make. If we could tap into it, a feat far beyond our current tech, it would dwarf the total energy humanity has ever used. Some science fiction stories play with this idea, turning black holes into power plants. Reality is less accommodating, but the physics allows the dream. Spin also changes how the final black hole warps spacetime for passing matter. Around a non-spinning, Schwarzschild black hole, the innermost stable circular orbit, ISCO, is 3 times the event horizon's radius. Around a maximally spinning Kerr black hole, that orbit can move much closer, just over the horizon itself for matter moving in the same direction as the spin. That means matter can fall deeper into the gravitational well, releasing more energy before it disappears. In an accretion disk, this makes for a much brighter, more efficient engine. Historians still argue whether most black holes are born spinning rapidly from stellar collapse, or whether their spins are built up primarily by later accretion and mergers. Gravitational wave astronomy is starting to weigh in. Some detected mergers suggest black holes with spins that are misaligned or even close to zero, while others hint at more aligned, faster spinning origins. The population is a patchwork, and the debate is very much alive. You drift closer, imagining the precise moment your two merge. For a fraction of a second, the remnant black hole will be misshapen, vibrating with the energy of the collision. But it will settle quickly, shedding those distortions in gravitational waves during the ring-down phase. What's left is a perfect Kerr black hole, spinning with whatever momentum the cosmic math decided was fair. Quirky tidbit: if the merger involves very unequal masses, the smaller black hole can act almost like a mallet striking a spinning drum, adding a sharp kick to the final spin. Depending on the angle, this can even cause the remnant spin axis to tilt, changing the direction of any future jets or accretion flows. In some galaxies, that tilt might explain oddly bent radio jets seen in active nuclei. Your pair will leave no visible jet when they're done, too little surrounding gas, but their spin will still matter. It will dictate how the remnant interacts with any future matter that wanders too close, and it will be a crucial clue for the astronomers who someday decode their chirp. Spin is the ghost of the merger's choreography, lingering long after the music stops. And maybe that's the most poetic part of this after-party. The black hole won't remember the individual motions of its two predecessors, but its spin will carry their final shared momentum forever, carved into the very geometry of spacetime. The moment the two horizons merge is not the end of the story. It's the start of a strange, brief aftershock in spacetime called the ring-down. If the inspiral and merger are the build-up and crash of a wave, the ring-down is the foam and hiss that follows. It's the new black hole's way of shedding the last irregularities from its shape, settling into the perfectly smooth geometry described by the Kerr solution. From your vantage, the instant the two become one is a flicker in the geometry around you. For a fraction of a second, the merged black hole is not perfectly round. It's distorted, bulging slightly in places, rippling in others. Those distortions radiate away as gravitational waves, much like a struck bell ringing itself quiet. The frequency and decay rate of these waves depend only on the new black hole's mass and spin. This makes the ring-down phase a clean laboratory for testing Einstein's theory. Measure those two properties, and general relativity predicts the waveform exactly. Mainstream anchor. In GW 150914, the first gravitational wave event ever detected, the ring-down was faint but measurable. The data matched the Kerr predictions within the sensitivity limits of LIGO at the time. Since then, every clear ring-down we've seen has agreed with general relativity, though physicists still scrutinize them for deviations that might hint at new physics. Quirky twist. Some researchers have proposed that if the remnant black hole is not a true black hole but something exotic, like a gravistar, boson star, or wormhole, the ring-down could contain echoes, faint, delayed repeats of the signal caused by waves reflecting inside the object. These echoes would arrive milliseconds to seconds after the main ringtone, depending on the size and nature of the exotic surface. A few events have been tentatively claimed to show such echoes, but none have been confirmed. It's the astrophysical equivalent of hearing a mysterious bump in the attic. You don't know if it's new physics or just the wind. For your pair, the ringtone will be brief, milliseconds, maybe less, because they're small compared to supermassive black holes whose ringtones can last minutes. In that short time, the merged horizon will radiate away asymmetries caused by the collision. The waveform will be dominated by the fundamental mode, a single, clean tone in the gravitational spectrum, but there will also be higher harmonics, overtones that fade faster but can carry additional information. Detecting those overtones allows scientists to measure the black hole's properties even more precisely. You imagine the sound as a single, low bong in spacetime, not a vibration in air but in the fabric of reality itself. If you could amplify it into human hearing range, it might resemble the deep strike of a massive gong. The precision of that tone is almost eerie. Hit the same mass and spin, and the ringtone is identical every time, like a cosmic tuning fork. Quirky fact: gravitational wave astronomers sometimes describe the ringtone as the quasi-normal modes of a black hole. They're quasi because they decay over time, normal because they're intrinsic to the object's structure, like the resonances of a musical instrument. In principle, if you could measure enough modes from a single black hole, you could test whether its spacetime geometry truly matches the Kerr solution, or if there's an unexpected wrinkle. Historians still argue about whether the term ringtone was first borrowed from electrical engineering, where it describes the fatting oscillations in a circuit after a surge, or whether it simply came from the bell analogy. Either way, it's stuck, and now even the most formal research papers use it without apology. From your position just outside the merged horizon, the distortion is almost hypnotic. It's not light or sound, it's the warping of the paths you would take if you moved. The curvature smooths itself, the wrinkles vanish, and suddenly the geometry is steady again. The new black hole is now indistinguishable from any other of the same mass and spin, its violent birth already erased from the horizon's appearance. For distant detectors, the ringtone will be the last note in the gravitational wave signal. After that, silence, unless some exotic echo waits in the wings. But the silence doesn't mean nothing happened. The merged black hole's spin will keep frame dragging the space around it, and if it ever finds new material to feed on, the after party could flare to life again in electromagnetic light. You linger for a moment longer, knowing you're seeing something no human eye could ever truly witness. The ringtone is spacetime's equivalent of a sigh, short, precise, and final. And like any sigh, it says as much about what came before as it does about what comes after. Out here, you can watch the show in real time. Back on Earth, though, our view of black hole mergers is only as good as the tools we've built to hear them. And the tools are about to get much, much better. The future of gravitational wave astronomy is already taking shape: bigger ears, sharper hearing, and the ability to listen to a far wider range of cosmic conversations. Right now, the workhorses are LIGO in the United States, Virgo in Italy, and KAGRA in Japan. They've already pulled in dozens of confirmed black hole mergers, but their range is limited. Even at peak sensitivity, they can only catch stellar mass mergers out to a few billion light years. That's a lot of space, but it's only a fraction of the observable universe. Planned upgrades, LIGO A+ and Virgo Plus, will push that horizon farther, increasing the number of detected events by a factor of several. Mainstream anchor. In 2020, the LIGO-Virgo KAGRA collaboration announced a roadmap for next-generation ground detectors: the US-based Cosmic Explorer and Europe's Einstein telescope. These behemoths will have arms tens of kilometers long, capable of detecting stellar mass black hole mergers all the way back to the first billion years of cosmic history. They'll also capture subtler features in the waveforms, like higher harmonics and spin-induced precession. that today's detectors can only glimpse. But to catch the slow, deep rumble of supermassive black hole mergers, you need to leave Earth entirely. That's where LISA, the Laser Interferometer Space Antenna, comes in. Scheduled for launch in the 2030s, LISA will consist of 3 spacecraft forming an equilateral triangle millions of kilometers across, trailing Earth in its orbit. With arms this long, it will be sensitive to millihertz gravitational waves, the bass notes from black holes millions of solar masses each. LISA could hear these giants years before they merge, giving astronomers time to coordinate electromagnetic observations for any possible light show. Quirky twist: even before LISA, we might catch the background hum of countless supermassive black hole binaries using pulsar timing arrays, PTAs. In 2023, several PTA collaborations, including NanoGrav in North America and the European Pulsar Timing Array, announced evidence for a common, low-frequency signal consistent with a stochastic gravitational wave background. If confirmed, it means we're already hearing the overlapping footsteps of thousands of distant, slow-motion mergers. The future is also about speed. Right now, it can take hours for detectors to confirm a new event and alert telescopes. Upcoming upgrades aim to cut that to minutes, or even seconds, allowing rapid follow-up. For black hole, neutron star mergers, that could mean catching a short gamma ray burst in progress instead of arriving to see only the fading afterglow. Historians still argue whether the shift from one detection in 2015 to hundreds per year in the next decade will feel as dramatic as it sounds. Some say it will be like going from hearing an occasional whale call to recording an entire ocean's worth of songs. Others worry it could make individual events feel less special. But each merger carries its own secrets: mass distributions, spin alignments, formation histories, even clues to the nature of gravity itself. Quirky fact to tuck away: some researchers are already simulating what thousands of detections per year will do to our models of stellar evolution. The more black hole masses and spins we measure, the better we can map the life cycles of massive stars, the dynamics of star clusters, and even the metallicity histories of different regions of the universe. In other words, black holes might end up teaching us more about stars than about themselves. Your pair of black holes here is just one among billions. The odds are good that when they finally merge, detectors on Earth or in space will be sensitive enough to catch them. Maybe by then, our gravitational wave network will be global and orbital, coordinated with swarms of telescopes across every wavelength of light. Maybe the alert will go out instantly, and somewhere, an astronomer will be awake at 3 a.m., rushing to point an instrument at the patch of sky where spacetime is about to sing. You watch them circle again, feeling the weight of inevitability. By the time they collide, humanity's ears will be sharper, our reach longer, our patience rewarded with not just a chirp, but with the knowledge of exactly where it came from and what it means. The future won't just let us hear more black holes, it will let us hear them in context, as part of the symphony they've been playing since the first stars died. The 2 black holes ahead are now etched into your mind, not as mere curiosities, but as participants in a story that's been unfolding for millions of years. You've watched them circle, felt the subtle tug of their gravitational handshake, imagined the chirp their final moments will sing. But now, slowly, it's time to drift away. You ease back, letting the warped starscape straighten, their light less distorted as you gain distance. The pair is still there, still locked in their slow spiral, but already they feel like part of a wider picture. You realize that this dance is happening everywhere, pairs and clusters, in galaxies, in quiet interstellar voids, some fresh, some in their final breaths. You've been a close witness to just one. The space around you hums with what you now know to be the whispers of countless other mergers. Not loud enough for your ears, yet, but they're there, stretching and squeezing spacetime, each an invisible punctuation mark in the universe's long sentence. Somewhere behind you, Earth turns under its thin atmosphere, unaware of most of these events, but steadily building the instruments to hear more of them. Mainstream anchor for your thoughts. Since the 2015 LIGO detection, gravitational wave astronomy has transformed from a proof of concept to a routine observational science. Each new run adds more events to the catalog, refining our understanding of black hole populations, stellar evolution, and the behavior of gravity itself. Historians still argue whether this decade will be remembered as the moment humanity became a truly multi-messenger species, able to combine light and gravitational waves into a fuller picture of the cosmos. Quirky twist: there's a tiny chance that a gravitational wave from a distant merger could be passing through you right now. You wouldn't feel it. The stretch and squeeze would be far smaller than the width of a proton. But the idea is oddly comforting. The universe is constantly in motion, constantly folding its history into every point in space, including where you stand. As you drift farther, the black holes shrink to points of darkness in your vision. Eventually, even their gravitational lensing becomes too faint to notice. They're just two more entries in the uncountable catalog of things the universe is doing at this moment. Their merger will come, their chirp will sound, their ringdom will fade, and then they'll be silent, the remnant black hole sitting in spacetime's quiet until something else stirs it. You carry the image with you, not of the collision but of the patient spiral, the inevitability, the quiet confidence of two objects obeying the geometry they were born into. They don't know they're part of a science we've only just begun to practice. They don't care about catalogs or detection runs, and yet they will contribute to them all the same. You're almost gone from their neighborhood now, the background stars realigning into familiar constellations. Somewhere in your mind, you replay the highlights, the warping of light, the rise of the chirp, the promise of the ringdom. You think about the detectors of the future, the astronomers who will listen to these events with instruments sensitive enough to catch every overtone. You think about the chance that, decades from now, someone might hear this very pair in their final seconds and not realize you were here first. A last glance over your shoulder. The giants are still circling, still invisible except for what they do to everything else. You smile, not because you've solved their mystery, but because you've accepted that their mystery is part of what makes the universe worth wandering. You turn away and keep moving, letting the blackness ahead be just that, blackness, until the next strange, beautiful thing drifts into view. Somewhere behind you, spacetime keeps folding, and two black holes keep dancing toward the moment they will become one.